Fine.
Assalamualaikum, I back to Mr. Azri, and today we want to present about our integrated project. We are from Group 22 CE2. This is our group, and our group member is Timotheus, Puan Masita, and me, Haikal. Next. For the introduction, the main objective is to suggest a suitable plan of the steam power plant that can be used by Malaysian government to build in Lumut Perak by indicating the population growth and economical value, and then to supply enough electricity to a new Lumut naval base and its town based on the power output by the steam power plant using the steam as the main working fluid, and the power output would be 280 megawatt and greater. For thermodynamic part, we wish to determine the amount of heat required to run the system and the efficiency of the steam power plant. Next. Our goal of the project is to get to know in detail on how to apply the concept of thermodynamic 1 and proceed transfer knowledges to the project, and then to get their experience by solving an engineering problem and the brainstorming to get the desired outcome, and then to achieve the final power produced by the steam power plant, which is 280 megawatt of electricity. Next. This is our schematic diagram of the project, and the water is pumped to the condenser pump, and then the pump will flow the feed water into the boiler, and boiler will heat up the water to become a steam, and steam will flow into the turbine. After the turbine, the steam will flow into the condenser, and it will cool down by the air in the fast draft cooling tower, and the steam will be pumped back to the boiler, and the final generation of the electricity will be 313360.04 kilowatt. Okay, next.
The cycle that used in this cycle is Rankine cycle. The ideal Rankine cycle does not involve any internal reversible. It contains 4 processes, which is isentropic compressor, constant pressure heat addition, isentropic expansion, and heat rejection. Next. In our plant, 6 turbine and 3 generator, and each of pump, generator, and condenser will be used. Next. Our next component is pump. Assumption is it is adiabatic process, is steady flow, there's no change in kinetic energy and potential energy. Next slide. The water inlet and output are both in compressed liquid phase during the process, and the temperature will increase and slightly increase in temperature. Next. For the isentropic efficiency of the pump is equal to 0.892, and then the actual work required is 1.612 megawatts. Next. The next component is the boiler. The boiler assumption is it is steady flow rate, there's no change in kinetic energy and potential energy, there's a pressure constant. Next. The boiler heats the water to the superheated stream at temperature 540 degrees Celsius. Next. We get the Q in from the high seas, and then we use that to calculate the mass flow rate of the steam, which is 552.53 kJ per kg. Next. The next component is the turbine. The assumption of the turbine is it is adiabatic process, the kinetic energy and potential energy change is negligible. It is steady flow device. Next. The work output is equal to 313 megawatts. Next. The efficiency for the turbine is equal to 0.8525, and then we times with the work output, we will get the actual work output for the turbine is equal to 267.13 megawatts. Next. The next component is a condenser. Our assumption for condenser is it is steady flow rate, the work is equal to 0, the delta KE and PE is equal to 0. Next. The Q output that we calculate is equal to 1531584.163 kilojoule per second. Next is the thermal efficiency of this cycle is equal to 0.9074%. Next is Mashita.
So for the justification part, we are using Rankine cycle as a basis calculation instead of current cycles. So from the pump, we use a covered pump RSV, which is can handle high pressure until 10,000 kilopascal. So from the water purifier at 1 atm, the pressure of the water will be increased to the 3,000 kilopascal, which is fed to the boiler and produce the work. In order to increase the efficiency of the pump, we need to increase the pressure of the pump. So next, for the boiler, we are using low sulfur grade coal, and then we use 133.2 kilogram per second and produce temperature 200 and 500 degrees Celsius. So from the feed of the boiler, the water is received from the pump, which is 3,000 kilopascal, and however the material of the boiler can only stand up to maximum 540 degrees Celsius. So we use the assumption 540 degrees Celsius, which is the heat is received from the water will receive the heat from the boiler, and then the temperature increase to 540 degrees Celsius, and the state of the liquid become a superheated vapor, and the heat lost to surrounding as it is not insulated well. Next. So for the turbine, we use an isentropic expansion process. In turbine, we use 6 turbines and produce 267 megawatt power, and then the isentropic efficiency with 85.25%. So from the boiler, the pressure of 3,000 kilopascal and 540 degrees Celsius of the steam will be rotate the turbine and having the pressure drop because the work produced out having the pressure expanding the mass against the turbine blades. So the phase of the outlet steam will become liquid vapor mixture as some of the steam condense at the surface in the turbine. So for the next is a condenser, which is related to the heat exchanger. The condenser will cool down the steam and change the steam into the liquid form to increase the efficiency of the pump. So as the steam enter the condenser, we are using the coolant substance, which is air at 20 degrees Celsius, and the outlet of the condenser will be back to 1 atm and 500 degrees Celsius in order to increase the efficiency of the pump. So next, for the total work of the manual calculations, we have the network is 265.5267 megajoule per second, which is megawatt, and the percentage error output is 5.17%. So in order to increase the efficiency, we need to decrease the percentage error of the desired output. So next is the recommendation.
Okay, so here are a few recommendations that can be done to the system. Firstly, in order to maximize the thermal efficiency of the Rankine cycle, the pressure of the condenser needs to be decreased. This is because the temperature of the steam would subsequently decrease too, which represent the heat rejection temperature. As a result, the work would increase. Next, we can increase the boiler's pressure. The boiling temperature of the steam rises when the system is above a required pressure. The plant is bound to have a higher thermal efficiency. Next, a feed water control system needs to be built. The feed water control's goal is to provide enough water to the boiler to keep up with the evaporation rate. Lastly, in order to increase the plant's efficiency, we must increase the boiler's efficiency. The combustion system's job is to provide adequate thermal energy while maintaining the boiler's efficient and safe operation. Therefore, we have to build an economizer to preheat the inlet water before the combustion. This can prevent the thermal shock and damage of the boiler by directly feeding the cold water into the main part.
So for the last part is the conclusions. To summarize the project, we had to almost achieve the target of the electricity electricity power, which is 267 megawatts, which is almost approaching 280 megawatts. So with the Rankine cycle and energy balance, we are almost reached the goal of the project, which is consisting of steady flow, isentropic devices, accompanied by accurate assumptions of the temperature and pressure for each devices. So before we finish our presentations, we would like to thank you to Mr. Azri for the dedication and efforts and teaching throughout this semester. Thank you.